The last component of lesson 8.4 is the ratio test. It suggests that we take a look at the nth plus 1 term divided by the nth term in absolute value and see where that goes as n goes to infinity. The nth plus 1 term you get by replacing n with n plus 1. Most often the absolute value doesn't matter if we drop the alternating n sign, and if we're determining the limit with n being positive anyhow, it's going to come out positive. But here are the parts. If that limit, the ratio of the nth plus 1 term to the nth term, is smaller than 1, it basically behaves like a geometric where r is less than 1, and therefore it would converge. We're seeing where this ratio goes and seeing if it behaves like a geometric. If it turns out that the limit is bigger than 1, of course in a geometric, if r is bigger than 1, it does diverge. Obviously the same would be true if the limit's climbing to infinity. That would tell us that the series is divergent. If L is equal to 1, that does mean that the test fails, and we would try a different test. By the way, when it does converge, that means that it converges absolutely and therefore converges. So when it asks in homework about absolute convergence, it does imply that you should do the ratio test. We'd like to do a couple of examples. The first is n cubed divided by 3 to the n, alternating in sign. We don't need to expand terms out, but you would put n equals 1 in here, n equals 2 in here, and write it out. And we're trying to decide if that sum is convergent or not. We begin by getting the nth term, and we put in n plus 1 wherever we see an n. Since we're taking absolute value, we might as well ignore the alternating n sign to begin with. So absolute value of the nth plus 1 term divided by the nth term would be n plus 1 cubed, again replace n with n plus 1, divided by 3 to the n plus 1. And then that would be divided by the nth term, but rather than creating a complex fraction, it'd be faster to just multiply by the reciprocal right away. So 3 to the n over n cubed. Once again, it is absolute value, but we're going to simply drop the use of the negative and the alternating n sign. N is positive, so the value is going to become positive anyhow. Continuing with some algebra, we would probably want to group together the cubes, and we can write it as n plus 1 over n all being cubed, and put the powers together as well, 3 to the n in the top. 3 to the n plus 1 we could break apart into 3 to the n times 3 to the first. And we want to do as much algebra as possible on this and then do the limits, so the 3 to the n's do cancel. We'll get a 1/3, and this we could divide by the highest power of n. So if I divide everything by n, I would get 1 plus 1 over n and another 1 over n cubed. I'm sorry, n over n. We still have the 1/3. And as n goes to infinity, this denominator is 1. As n goes to infinity, this would approach 0. We take it times 1/3, and yes, this does equal 1/3. So this is as n goes to infinity. So we have the limit. It's 1/3. Certainly that's smaller than 1. And so by the ratio test, this series, the original, is convergent. Another example involves factorials. This can sometimes be challenging because we haven't done a lot of work with factorials. N to the n is the numerator. N factorial is in the denominator. N goes from 1 to infinity. Again, we're not going to write terms out, but we're trying to decide if the sum is convergent or not. We'll divide the nth term and the nth plus 1 term. The nth plus 1 term we get by replacing n with n plus 1. Another one of those scenarios where n is positive, so we really don't have to have the absolute value. It's going to be positive anyhow. So we'll have n plus 1 to the n plus 1 power over n plus 1 factorial. So we're simply replacing n with n plus 1, and that's how we get the n plus 1 term. Now, once again, you should divide that by the nth term, but that would create a complex fraction, so it's okay, it's allowable by me to simply multiply by the reciprocal of the nth term, n factorial, n to the nth. Similar to the previous problem, we want to group together sort of the like components. So the powers we would want to put together, and then the factorials we'd want to put together. We could tear this guy apart into n plus 1 to the n and n plus 1 to the first. Let's write it as n plus 1 to the first times n plus 1 to the nth. That's tearing this guy apart. We'll put the n to the nth in the denominator. And in the numerator we have n factorial. And we have n plus 1 factorial. So that's a number that multiplies down to 1. So we could break that apart as well, n plus 1. And the next number down would be n on down to 1. We could write it as a factorial after that. So n plus 1 times n minus 1 all the way down to 1. So the n factorial components would cancel. And the n plus 1s that are left to the first power would cancel. We would then be able to rewrite this as n plus 1 over n, all to the nth. Since they have the same exponent, we can combine them and raise them to the nth power. And it's common that we divide by the highest power of n again. So divide each of these by n. So 1 plus 1 over n, and n over n would be 1 raised to the nth. And now if we take the limit as n goes to infinity, this would approach 0. And 1 plus 1 over n to the nth power, you might be inclined to say this would go to 0, so we'd have 1 to the nth. But this is a definition of the number e. So it actually approaches the number e. Let's put it over here. As n goes to infinity, that is one of our definitions. Of course, e is around 2.71828, ... bigger than 1. And since that is greater than 1, this series diverges.